Hi, everyone. Thanks for joining.
Join via audio. Is that what you want?
I want to say that's the one we did the first time, but I guess we'll just
try it.
We'll just do it again.
We will get started in a few seconds, everyone. Thanks so much for joining, and thanks for your patience this morning or afternoon, wherever you're calling in from.
There we go. 6.
Your mic is hot.
So we will go ahead and get started. So again, welcome everybody to today's Ask Me Anything session, focused on the advanced manufacturing and robotics subtopics under the 2025 NASA SBIR Ignite solicitation. I'm Beth Bacareza, and I'm part of the Ignite team through my work at BMNT, where we help startups navigate to and through the SBIR Ignite initiative and help unlock commercial opportunities both in space and here on Earth. Before we dive in, a couple housekeeping notes. So first, the session is being recorded, and the replay will be available on the Ignite website shortly after. Please use the Q&A box to submit your questions at any time, and don't forget to upvote the ones that you would like most answered. This will help us choose the most relevant questions, at least for the group as a whole. And lastly, we'll launch a few quick polls during the session to help us get to know you and your work. So please do answer the questions in those polls. It helps us get to know you and tailor these sessions to your needs moving forward. So we'll first kick off with a brief Ignite overview. And to that end, I will hand the baton over to Dave Truitt, SBIR Center Liaison to Marshall Space Flight Center. So Dave.
Thank you, Beth. And thank you to Beth and her team and everybody at BMNT for hosting these AMA sessions. I think they've been really beneficial for Ignite program. We appreciate all the work they put into it. Thank you also to our topic authors and their teams for taking time out to be with us today and help out our prospective or interested applicants for this program. And finally, to those attending, thank you for taking time to come out and join us. Hopefully this will be beneficial for you. For those of you that are new, we're going to go through a few slides real quick and just give you a very brief introduction to the Ignite program in case it is your first time experiencing this program. So on our next slide, we'll talk about what are the key differences. I believe we're going to talk about the key differences between Ignite and SBIR mainline program. Assuming somebody's got control of the slides, because I don't think I do. Or do I?
Yes, we should be on the next slide.
There we go. All right, fantastic. All right, what makes SBIR Ignite different? Well, all of our SBIR programs have a goal of infusion into NASA and using that technology, but Ignite is different in that it focuses on commercialization, trying to move technology and solutions quickly into the commercial space. We achieve that through a few different ways. You see, we have smaller cohort compared to mainline, much smaller. A fraction of the total proposals will be awarded for Ignite versus mainline. We use entrepreneurial engagement through our friends here at BMNT. You can join their Slack channel, Catalyst events and coaching, and we'll have more information on that on another slide. We also use an accelerated schedule. So if you do apply and are awarded, you'll need to note that phase 2 proposals are due the 4th month of the phase 1 period. So we're trying to keep that process moving as quickly as possible. We also encourage a shortened performance for phase 2. If somebody's got a hot mic, you can mute that for. Thank you. All right, next slide. This is a quick overview of the Ignite program. And if you're familiar with SBIR, you'll see it's the exact same framework. We have 3 phases. Phase 1, 6 months, awarded up to $150,000. Phase 2, 24 months, up to $850,000. And phase 3, which is commercialization and is funded through non-SBIR funds. You also have the same options for I-Corps through NSF and TABA, Technical and Business Assistance Funding. And that money goes in addition to the award amounts for those phases. We also have post-phase 2 opportunities that typically require matching funding. So those are opportunities you can look at post-phase 2. Next slide. Here's just a quick snapshot of some key dates for this solicitation. It opened on June 2nd, so we are in a blackout period and we cannot answer specific questions about proposals. Key thing to remember here, July 22nd, submissions close at 5 p.m. Eastern time, and we'd expect award in fall, which would be late 2025. Next slide, please. All right, today is our next to last AMA. This coming Thursday at 10 o'clock or 10 a.m. Pacific time. We have an AMA for radar, low cost millimeter and centimeter wave radars for exploration. So hopefully have a good turnout for that as well. And of course, all this information is available on our nasa.gov/SBIR website. So please go there and look for additional information. And I think our next to last slide will have some more information that we can pass along to you, or does it not? Yes, it does. So we have our newsletter. We encourage you to sign up for that at nasa.gov/SBIR-STTR. You can also go there to get recordings of these AMAs. You can also join BMNT's Slack channel at the link provided there, so you can stay up to date on community building activities. And of course, NASA is not the only SBIR program in the game. If you go to sbir.gov, you can see other federal agencies that participate in this program and check to see if they have opportunities that align with your mission and your goals. So I believe that is the last slide, other than questions. Yep. Any questions real quick, Beth, before we move along?
Yes, let me do a quick run through of the questions that we have so far. So one moment. So there's one question that asks, can we include links in the proposal to external sites such as YouTube videos?
My understanding is no, but the solicitation outlines all requirements for the proposals, and you can go there for specifics on that. But
great, thank you. And then is one question asks, is this SBIR only or is STTR a possibility?
This is SBIR only and is the Ignite cohort of the SBIR. So yeah, STTR is typically gone through with our SBIR mainline solicitation. So I think that has already passed for 2025.
Great. And the last question before we move on to the actually two final questions before we move on to the subtopic overview. So does NASA encourage dual use technologies that serve both Earth-based applications, for example, FEMA, disaster zones, and future in-space missions?
In general, yes. Yeah, NASA certainly has applications that are, for space and Earth equally. Obviously not particular to this solicitation, but in general, yes.
I think that's one of the kind of core criteria for Ignite is that dual use component potentially.
Yes. Yeah. Thank you, Beth.
Of course. All right. Last question before we move on. How many awards do you expect to issue for this topic, if you can say? That's my add-on at the end.
Yes, I think we had that in one of our slides. I think we expect 15 awards this year for Ignite.
Great.
Of course, that always depends on funding and that type of thing. But yeah, that's kind of our goal.
Great. Thank you. Actually, and one final question, and then we'll move on. All right. Can two companies collaborate on a proposal submission?
Haley, are you there? I'm 99% sure joint ventures.
Yes.
As long as we meet yeah.
If you have questions about eligibility, there's a lot of detail in the solicitation and in the links within the solicitation to some of the requirements. But yes, the answer is yes.
Yeah.
All right, thank you. Okay, so we'll come back to some of the questions related more to Ignite in the proposal, but to stay on time, let's go ahead and move into our subtopic overviews. So over the course of the next three kind of segments, we will dive into the three subtopics featured in this year's solicitation under advanced manufacturing and robotics, respectively. So first, I will hand over to Jabrail Mohammed, who will go over the first advanced manufacturing subtopic. called Advanced Real-Time Monitoring and Control Technologies for Additive Manufacturing.
No, you'll just.
Good morning. Is my sound coming through clearly?
It is, yes.
All right. So, good morning, everyone. I am Jabril Muhammad Jr. I will be presenting on the advanced real-time monitoring and control technologies for additive manufacturing. Go to the next slide. So, looking at in-situ monitoring in itself, it is the real-time observation of the manufacturing process. It utilizes sensors within the build chamber to characterize the dynamic state of the manufacturing process at the melt pool, layer, or component scale. Now, it enables detection defects in real time.
Do we have Jabril on the line? We lost you.
We're working it back.
Perhaps so while we sort through these presentations, why don't we go ahead and skip to Greenfield? And we'll shift to the third subtopic. So if we can shift to those slides. And Greenfield, we'll bring you on to discuss the robotics subtopic. So Greenfield is Project Manager ARC LSI, which stands for Autonomous Robotic Construction of Lunar Surface Infrastructure, to talk about, again, the robotics subtopic, modular scalable robotic subcomponents to unlock scalable robotic manufacturing and assembly in remote, challenging environments. So Greenfield, over to you.
Thanks, Beth. Thanks everyone for coming. So if we go to the next slide, the gist of what we're trying to do in this subtopic is really kind of develop that supply chain for robotic components so that we can implement space robotics for servicing manufacturing assembly a lot more quickly and more cost effectively. And there's a lot of open questions on how do you do that. So that's what we're kind of hoping that you guys can help address and figure out what are the problems, what are the things that we need to do to kind of enable that capability more robustly. So in the near term, there's a lot of ongoing discussions and potential for missions related to implementing robotics for different types of missions. So being able to have standardized components that are ready to implement into missions and start executing is a goal of the agency. And being able to use robotic components that don't take years to acquire and purchase is kind of one of the major goals. And that it's not just motor components, but a lot of the different types of components that are needed to enable these types of capabilities and address functions like orbital capture, drilling, joining, manipulation at different scales, and more. And being able to figure out to be able to address the mission needs, not only at the larger scale missions, but at the smaller scale missions like small sats and on the lunar surface and Mars surface, trying to figure out what can you standardize across those interfaces and environments to be able to address that ecosystem and supply chain a little bit better. So what's kind of in scope and what's out of bounds? So I think in the long term, if we're successful to be able to design an economy where we have lots of robots kind of working all together and figuring out how to build infrastructure, do manufacturing, do exploration, and all the things that we would like to do in space. So solutions that can be repaired, can be assembled robotically are encouraged. Solutions at scale for small set and orbital surface aggregation applications are of large interest. And then robot architectures that are non-specific. So for inchworm or climbing robots, rover-based systems, free flyers that can address different types of mission needs and architectures is encouraged as well. And then there's also a lot of work that's been done within the agency to develop robotic systems. So adapting and qualifying existing hardware to the commercial market is encouraged. So hardware like that was done within OSAM-1 or through the IPEX rovers or different projects. Those things that make sense to be integrated into the commercial market would to increase the options in supply chain is what we're kind of looking for. And then what kind of solutions and approaches are welcome? So trying to really address the economies of scale. I think there's always been, within the space economy, there's always been a demand problem. So how do, even if there is a short-term demand or like a near-term demand problem, how do we get ready for scaling up to much larger scales and facilitating that robust supply chain? Trying to figure out interoperability and standardization, leveraging the work that's been done terrestrially to apply it to the space economy is where we kind of want to go, and getting ready for that capability. So products at different scales, small, medium, large, to address different types of mission needs from small sets to larger scale missions and beyond that. Trying to figure out how to integrate and address the environmental challenges of space, such as dust and lunar dust, resilience to thermal radiation, UV, and those other environmental challenges that we normally deal with in space, and trying to address those capabilities, those needs for the robotic actuators and other components that are needed to enable a robotic ecosystem. And I think the last thing, I think that's the last thing I kind of wanted to say. I'm going to pass it to Therese to kind of give some images and talk about, give a little bit more detail about some of the things that we're thinking about. Therese, are you online?
Yes, I am.
Okay.
I'm not going to put on my video because I'm going to have bandwidth problems. So I'll just go ahead and talk. A couple slides here.
Yeah, you can go to the next slide.
There. Okay. I've worked on, I've had the privilege to work on 2 of the rovers, not directly, but it was in support of them, an instrument that we were putting on the rover. And also I've worked on OSAM-1, which was a servicing mission. We were unfortunately canceled, but the servicing mission is the spacecraft and the robotic system is pretty well built. And we were going to be servicing Landsat, which is is at the end of its lifetime. And we were going to go and fuel it. And we built a lot of components in support of that, along with Maxar, who was our partner in this whole mission. So in any case, you kind of can see enabling a new era. And this particular thing is all the possible things. This is for robotics in space, where you're dealing with orbiters, right? And you could see all the different possibilities of different kinds of missions we could be doing with a spacecraft like OSAM-1. And like you have to grapple the satellite, you'll see different things here. And if you blow this up, you'll be able to see all the different applications that are possible, or even more. But it just gives you an idea of the kinds of things we like to use robotic arms and robotic capabilities. So we could go up and service satellites, extend life of satellites, join satellites together, do manufacturing in space, especially with the Gateway project on the lunar projects. There are things that we want to assemble in space and then use them as parts of space stations or servicing stations. So there's a lot of possibilities with robotics here, and if we're really lucky, can embrace our nation's vision. There would be a robust market for different types of components in the future, if everything goes well. And the Mars rover, you can see a picture of the Mars rover here. And this is an example of highly complex robotics that we do. You can see in the front here is the drill, and it's extremely complex. But there are other things that are a little bit easier or more brute force kind of designs, like the this rover, the IPEX rover. And you have this is an example of robots that are designed to assemble, be assembly robots and assemble more robots. And this is another example of the kind of the idea that we have. We'd like to develop off the shelf robotic components that can go together as an integrated system, where they have defined interfaces, and you can make some custom parts if you'd like, but the interfaces to all the different components, actuators, the motors, the different components are standardized, so you can kind of buy them off the line, off the shelf, and have easy assembly, kind of like a Lego system. So you can go to the next slide. And here you can see some more of the kinds of components that we deal with. You can see actuators. You can see how complex they are. But one of the challenges we have is these are the some of the arms for one of the arms, and you can imagine if you're on a planet and you have dust, getting dust in all these different components would be a problem. So having dust, shields and things like that that are part of your designs would be really important. Again, that interchangeability. These shows you some of the electrical harnessing we use, which is rigid flexes in some of the designs, not all of them, but some of them. But then again, if you've got Kapton here and it's a light layer of Kapton, you can imagine the dust would erode that. So we're looking at things that can, give us more robust harnessing and keep and make it easier to manufacture, right? These are spools that allow the robotic arms to turn, which is kind of common in most of the robotic systems where you have arms and things. And then over here at the bottom there, you see another totally different type of art robot. It's a snake robot, and they're kind of fascinating in how they can navigate and like a snake and actually climb up things. So you could, have tools that attach to it, and all the components for it that would make it longer or bigger or whatever. You could have a line of those things. So our goals kind of have like a Sears line of tools where it's interchangeable. That kind of thing that could be offered to the space community. Like we have many manufacturers now that build antennas or star trackers or different things that people go and buy them off the shelf, rather than reinventing the wheel. So that's the goal here, is we want to try to help developers of missions be able to have components they can put together without having to redesign every time they do it. Because right now, almost every one of these are going to be unique in what NASA's been doing. So that's it.
Great, thank you. So a few questions before we shift to the next subtopic. So is this robotics subtopic specific to certain types of manufacturing, or is it general?
I would say it's general. I think we want to be able to address like a lot. There's been a lot of development in welding technologies and different types of reversible joining technologies. So I think it's going to be a task to try to figure out how do you design a system that can address multiple. Oh, I can start my video. Yeah, to address multiple needs and trying to find the market for that. Yeah, I don't know if that answered your question. So it's not a specific technologies to address, but across that spectrum.
If the individual who submitted that question has a follow-on question, please do put that in the chat. Perhaps two more questions. So can you clarify what you mean by robotic subcomponents? Are you looking for actuators, motors, resolvers, other?
Any and all of the above. But we're looking at something that can be off the shelf and be used by people in one of the environments we specified, planetary or orbital. And there's different challenges with different environments. And that's one of the things I could recommend folks to do, is to get familiar with future missions for NASA and target a mission or something and say, oh, okay, this particular motor or this particular actuator would work, and I'll have a line of them, a couple different sizes maybe, and you've done the homework on that to make sure that they can survive all the environments. So you might have an existing line that you want to upgrade to space grade, that it can work in space, or you might design something specifically and just design some components that could be used by multiple missions.
Yeah, there's also this question of modularization of robotic components in a way that makes sense to make implementation of missions that need robotic capability faster and more cost effective. So it spans that whole spectrum of from the architecture to like modules or to subcomponents.
Yeah, if we could go back to the previous slide, back up one slide. That you can see in this bottom picture, that's kind of the kind of thing that would be interesting, was to be able to have this capability to have different options, and you could put the parts together in different ways. Kind of like a Lego system. You can kind of mix and match parts and put them together and get different configurations. That would be interesting.
Great, thank you. Perhaps two more, and then we will move on, but we'll come back for more questions at the end. So for this subtopic, how much detail, and perhaps Haley, if this is getting too specific to a company, do jump in. So for this subtopic, how much detail should the proposal include regarding the specific target applications?
I think it'll depend. I think enough to understand like what it actually is being developed and what technology is actually being advanced, and seeing how it could be applied. I think infusion is an important part of how the technologies get developed and where they ended up going. So I think that's kind of a case by case type situation. But the more information, the better.
Are there required or ideal entry and exit TRL and MRLs for phases 1 and 2? And that exit TRL, MRL for phase 2 are both 9?
I think there's an actual definition and expectation on each of those for phase 1 and phase 2, because the funding levels are that are appropriate for each level. I think, I'm not sure, don't quote me on this one, but I think phase 1 is going to be from 1 through 3 or 4 or something like that, and then phase 2 is probably up to 6, and then after that it's going to require flights and operation, and that's much higher levels of funding. I don't know if anyone from SBIR can expand that maybe a little bit better.
You did a great job, Greenfield.
Thanks.
Final question, and then we'll shift. So are specialized subsystems encouraged, or is the intent to develop complete systems?
I think a specialized system, like say actuators, if they came in several different sizes and could be, incorporated in with other designs, that would be good. Because there's a lot of challenges that, say if you got the more environmental challenges you can address, the better in that case. Like if you have an actuator that can handle a dust environment, radiation environment, atomic oxygen, your lubricants are good for long life, right? In vacuum, because they can be evaporating. You have motors to develop a motor product that is reliable in different sizes, different torques. All of that kind of thing could be useful to somebody and could be incorporated into designs. Or you could have a whole entire setup where you have all you design actuators, motors, tubes, arms, structural components, and it's a plug. It's a kind of a plug and play and a erector set kind of thing where you can just configure it however someone would want, and they'd have off the shelf. I think both of those kinds of concepts would be very unique, very interesting. And that's it. And the goal again is to have that off-the-shelf component that can be used by multiple organizations.
Yeah,
And
Great.
I also want to echo what the kind of the core Ignite principle of infusing into the terrestrial industry and trying to have that streamlined process from terrestrial applications to space applications in the different environments and making that process from applying some of the terrestrial technologies that we're developing into flight a little bit more smoothly and make the transition easier. I think that's something interesting to look into.
Great, thank you. All right, thank you, Greenfield. Thank you, Therese. We will go ahead and move on to check. Do we have Jabrail? Okay, how about Louise?
They said they
Hey,
dialed.
Beth, can you hear me?
Oh, yes, we can.
There we go.
Where's the music?
Okay, excellent. So we will go ahead and shift to the first advanced manufacturing subtopic. So Jabrail, over to you to provide an overview.
Yes, am I coming through fine?
You are.
All right, so sorry for the interruption. So we will be discussing advanced real-time monitoring and control technologies for the additive manufacturing process. So looking at our proposed solutions, we'll begin with the capability of real-time observation of the manufacturing process via in-situ monitoring. Now, we propose to utilize sensors within the build chamber to characterize the dynamic state of the manufacturing process at a melt pool, layer, or component scale. Now, by identifying the anomalies as they occur, we will be able to correlate them to some common AM defects, such as porosity or lack of fusion. Now, looking at the control portion of this, we will be able to use the real-time data to automatically adjust process parameters during fabrication. Now, being able to do this allows us to mitigate defects on the fly. So we will then be able to develop the capabilities to increase automation during our AM process. The applications of AI and some machine learning capabilities will enable closed loop control to increase efficiency and yield while decreasing the need for manual check-ins during the AM build process. So we aim to reduce post-processing. Now, we do so by minimizing the need for extensive inspection and rework. Now, currently, traditional non-destructive inspection capabilities are limited when it comes to AM parts. And that is due to the complex features that can be found in some of the parts that are produced. So we then will end goal look to enhance material qualification by providing a pathway to certify new AM materials more rapidly. Now, this will require some scientifically validated correlations between process signatures captured by the in-situ sensors and the critical end-use properties of the manufactured part, this being mechanical properties or even fatigue life. We can go to the next slide, please. So what are we looking for? Two things: process control function and part quality function. Now, through the process control function, that hits on the real-time warning of build problems or process deviation that in-situ monitoring can detect. Through the control portion, we can monitor the effects of parameter changes or even some of the spatter conditions that is coming with the AM process. Now, that will improve the part quality function, where we can then conduct quantitative analysis of part quality. So we will address technical risk through part quality improvement, through certification of the AM space hardware, and most importantly, we're looking to qualify in-situ monitoring as a NDE method. So once you couple all this together, we can then introduce the capability for more automation in our in-space applications. So it's commonly known that AM can reduce cost. However, there are still some hurdles to address in that path, such as reducing waste, or even being able to make this a more wider adopted technology for high value applications. Now, we're looking to also address this by reducing some of the schedule through eliminating some of those post-processing steps, such as HIP or our NDE, our traditional NDE. So how do we expect to achieve this? For one, we need improved sensor technologies to be developed and analyzed. Once we incorporate multiple sensor technologies into a multimodal sensing system, we will need some type of software solutions that integrate sensor input from the different data types that will be generated from our sensors. So once we have that holistic view of the AM process, we can then begin looking at some known correlations between those indications that the sensors are able to detect, the physics of the process itself, and then finally the actual defects in the finished part. Now, all of this will require advanced data analytics, as I mentioned before, through the use of AI or machine learning algorithms. And then we would then have our final product that we aim to achieve of real-time feedback control using AI algorithms to detect and correct defects during the AM build process. We can go to the next slide. So I think we have questions.
So there were a couple questions about how you define additive manufacturing. So for example, do you define additive manufacturing as 3D printing only, or is the definition open to other types of additive manufacturing?
So we have a broad definition for AM. Some of our current applications can be seen in like laser powder bed fusion, even directed energy deposition, some of our DED processes for our more metal components. But as for right now, that is more broad terminology.
Are you also considering non-fusion AM processes, for example, solid state, for in situ monitoring?
Yes.
Okay, we'll do 2 more questions and then we'll jump to the next subtopic. Again, then we'll jump back to questions at the very end. So is this just sensors or using the inbuilt cameras that are usually embedded in 3D printers? So computer vision can be used with camera to adjust the printer in real time.
So essentially, we will combine the capabilities of sensors that can be added to the machine and also those that are readily available with most AM machines. That's why our multimodal system portion will come in, to where we're able to integrate all of that data into a model that can give us some type of idea of the build integrity of the part.
Great. And final question for now. Is this subtopic limited to just LPBF, or would wire arc, DED, or thermopolymer extrusion be sufficient, I assume is the end of that question, or work?
Yes. So process-wise, we are opening up to laser powder bed fusion and DED. However, we will be focused more so on metal applications of materials.
Okay, great. All right, we'll jump back to questions related to the subtopic, but meanwhile, let's move on to the next subtopic. So Louise, do we have you on?
I think so. We're trying to share a computer here.
Excellent.
Given some of the difficulties we had with the conference room microphones. Apologize for that. But if you can hear me, then I guess we're good to go.
We can, and we'll rename your square there. So yes, over to you, please.
Okay, so the subtopic I'm here to talk about today is computational design of new materials, processes, and products, leveraging the microgravity environment of space. And next chart, please. Importantly, that is leveraging the microgravity environment of space and not necessarily in the environment of space. And so it's maybe a little broader than it may sound to begin with. And I cannot start video, so that just did a thing. Okay, so this topic seeks technologies that use integrated computational materials to develop next generation materials, manufacturing methods, and new products that benefit from a microgravity environment. We're really looking at leveraging the understanding that we have been able to gain largely through microgravity experimentation as a major part of it in some of the physics-based phenomena involved in solidification processing, going all the way to the structure and properties of the materials that are developed. We've leveraged that microgravity space environment for in-space manufacturing and really for a fundamental understanding of some of the solidification processes. And so it's really kind of as broad as both of those things. But then by integrating models across different scales, ICME can predict vital microstructure structure and properties of space manufactured products. And also that will enable terrestrial material exploration on Earth. The proposal should focus on using ICME to develop next generation materials, processing methods, and improve understanding of mechanisms involved in material transformations, advanced materials discovery, test processes, or manufacturing methods of novel design and synthesis techniques to rapidly help scale and transition these efforts to industrial partners. Yes, I just read that because there's a lot of content packed in that one particular phrase. Happy to answer questions about it, but we really do have a fairly broad and deep topic here. On the next page, I think this might help elucidate just a little bit more what we're really talking about. We're looking for things that can either enable commercially viable and sustainable opportunities actually in low Earth orbit, developing and processing materials there. But we're also looking towards optimizing materials and structure for improved mechanical properties, and that can occur. I think we need to be on the next page. We need one more. We need next chart. I'm sorry. I'm ahead. We also can be talking about development and optimization of materials and structures that are then later actually, able to be manufactured on the ground based on the understandings that we draw from microgravity materials processing. We're looking specifically at materials and processing schedules then, though, that are compatible with or benefit from manufacturing in microgravity. Let's see. I got lost shifting from one platform here to another. I've got 3 computers going. And then providing better understanding of material structure and properties evolution during low Earth orbit manufacturing will lead us to efficient and robust qualification and certification of materials, processes, and components. And the really big kicker then is the technologies that extrapolate and interpolate between existing data and really leveraging particularly machine learning that is based upon physics-based models and basically we want to bridge between the high fidelity physics-based models and the lower fidelity but easy to field in a production environment data-driven models through means of additional sensors, post-process characterization of samples, anchoring data sets that can be extrapolated by machine learning. There's really a lot of different ways to do this bridging across time scales and length scales. And we're looking for a lot of that connective tissue really as a part of this subtopic. And so it's a little bit less prescriptive than I think some of the subtopics had been. One thing that might be particularly useful to proposers is there was a recent NASA TM that was published that is openly available. You can see a little bit more about some of the work that we're doing and what the different things that we're trying to bridge between are. And I can put that TM number in the chat, and people are welcome to go out and read that in its entirety. And I think that will hopefully provide a little bit more insight. Any questions?
Yes, so there are a few. So I'll ask a couple, and then we'll go ahead and then run through the remaining questions in the Q&A chat. So what type of materials? Metallic, non-metallic?
I think primarily we are also looking at metallic materials at this point. There are some cases where we've used other analog materials to like mimic a metallic material, but we're really primarily looking towards metallic material processing and things that we would leverage. Semiconductors are also on the table. But primarily we've been using ICME. I think, and you'll see in the report, we have been primarily talking about metal alloys.
Great, thank you. How about processes that help detect materials in space, like minerals, gold, platinum in space, to then capture them in space? So basically, can this be part of space mining?
I mean, I think while we're adjacent to space mining, I think that's really a little bit outside of the subtopic. Of course, we have to be able to get materials in order to be able to process the materials. So you would potentially touch upon where materials might come from for specific material types that you might be interested in developing. You'd like to be able to obtain in situ materials either from recycled materials or something that you can get from an in situ environment. But that's really a little bit outside of the scope for the actual prospecting, I think, is outside of the scope of this subtopic.
Great, thank you. Are you looking for manufacturing processes in low Earth orbit as well, or just the material itself?
Oh, I think we're looking at targeting manufacturing processes in low Earth orbit. So whether you would actually have to, pardon?
Lunar? Or is that outside of the field of it? Leo.
Oh, it's just, this is just Leo. So yeah, I think, yeah, it could be towards materials that would be manufactured in low Earth orbit, although with the time frame of this particular SBIR, we wouldn't really expect to have anything, have that turnaround. But but that is the intent. And yeah.
Okay, great. How can AI-driven materials discovery help in designing new materials that are optimized for both sustainability and performance under space conditions? For example, radiation resistance, biodegradability, etc.
That's a very good question, and that's exactly the sort of thing that we're seeking answers to. I think that there's a lot of different ways that AI/ML can be used on it. Everything from a discovery platform where you're looking at very low atomistic scale and bridging up and trying to understand more about predictive material properties from first principles, all the way to qualification of materials once you've actually developed things. So I think there's really there's a lot of potential for using AI/ML in or unique characterization methods, which is really what this is all about, and connecting those together to really make that materials discovery process a lot more robust and efficient.
Great, thank you. Okay, now I'll go back up in the Q&A chat box. And if you are the relevant subtopic author to answer that, please do jump in. And for those who will be sending in last minute Q&A for the next 10 minutes, please do indicate which subtopic your question is related to. I think I've done a decent job mapping out which questions further up in the chat are related to which subtopic. Okay, so for the robotics subtopic, are you interested in, I think we may have perhaps covered this a short while ago, but so are you mainly interested in robotic systems or subsystems or capabilities of manufacturing individual components? Sorry, are you interested in robotic systems or subsystems or capabilities of manufacturing individual components also of interest?
Yeah, I think we answered that one earlier, and it was the answer was kind of that whole spectrum and trying to figure out what makes sense to really help tackle the supply chain problem and the availability of components and the cost of components, and yeah, not particularly choosing any area.
Okay, great. What qualifies as getting an existing technology ready for space? Are there any specific testing procedures or certifications required?
Yeah, typically for qualification for the space environment, usually each space environment, depending on where it is, like Leo, Geo, Lunar, Mars, has their own set of requirements that need to be qualified for flight. And I think I think there's a lot of literature out there, and I think working with I think there's NASA standards out there. I'm not totally sure which ones off the top of my head that are needed to help qualify components for SpaceX, but it really depends on the environment that you're trying to target the materials for.
Great, thank
I
you.
don't know, maybe Therese or Giuseppe, you guys might have a better answer.
There's some standard packages of when we do, calls for full of spacecraft and things. There's a standard package that has all the qualifications. That would be like the Goddard Gold Rules, design guidelines, design handbooks, and they're online. And I think you don't have to design to that right now, but you should be aware of it because you at least know, oh, gee, this might outgas a lot. I'll never be able to use it in a vacuum, right? So you'd be aware of the kinds of problems that you can have, and you won't, base your design on something that will never be able to fly. But there are other aspects of qualifying parts that can be done later on, as long as you get the right basic materials to start with. So that's the key thing is I don't know if we can supply or if we can add to the call a list of references just so that they have a sense of where to go for it. Would that be possible to put that out to folks?
We can provide it in the responses to the questions that we put out, so we can include those links there.
Yeah, just some general guidelines. So you just have a sense of something, so you don't propose something that's a non-starter at the get-go.
Are optical sensing technologies for robotics and spacecraft proximity operations appropriate for the robotics subtopic?
I think so. I think we're trying to target particularly the surfacing capabilities and manufacturing and assembly capabilities, but that is within scope as well.
Great, thank you. Dave, or Haley, a couple questions have come through asking if our proposed tech covers 2 topic areas. Should we propose to both?
You can only make one submission, and it is your responsibility to pick which subtopic is the most appropriate for your technology. But it is one submission per firm per solicitation.
Great, thank you. I believe this question is for Jabril and the team with the first advanced manufacturing subtopic. So the term in situ is misleading. Would you please provide additional information? Any embedded technology sensors is considered FOD, and if non-contract, may consider destructive. Do you accept any solution after part build in quality inspection?
So as far as the term in situ goes, we're looking for more like in process, online, in system type of system. So as someone mentioned earlier, some AM systems come with inbuilt cameras already. So for example, like optical tomography, some and visible cameras that come already in the system that just gives you a field view of the build chamber itself. So we wouldn't so much introduce FOD into the process. But it just gives us a way to better characterize what is going on with the process. You can even look at some cases where people have used X-ray systems implemented into the machine to monitor the behavior of the melt pool on the subsurface level. So we're looking, like I said, more ways to characterize the process from a melt pool, a layer, or even a component scale, and not so much post-processing. We're looking towards being able to qualify as-built parts as they come off the machine. So trying to get away from more of that post-processing that we're looking at now with current technologies.
Great, thank you. So we have just 2 minutes left, so we'll do rapid fire. For the subtopic related to ICME, is the 5th bullet point, if you can remember what that 5th bullet point is, limited to microgravity environments like the other 4 bullets, or is it broader?
I'm trying to on the chat.
All right, so
Can you? I can't multitask.
No,
Could you repeat that? I'm sorry. I was trying to add something to the chat and having struggling over there.
No worries. So is the 5th bullet is limited to microgravity environments, or is it broader?
I don't have the fifth bullet in front of me. Let me see what the fifth bullet is. Don't remember the fifth bullet. Can anybody
Can you remind us
expand
of
on what the fifth bullet
Okay,
might
it
have
looks
been?
like Garrett responded in the chat.
Okay, I just pulled the chat off. Okay. Okay, so do you mean the technologies that extrapolate and interpolate? And can you read the question again? I'm sorry.
The fifth bullet, is it related to microgravity like the previous four, or is it more general or broader?
I mean, I think it's still related to microgravity, but you may in some cases be interpolating and extrapolating between data sets that might have been obtained in microgravity, other things that you get on the ground. I think there's really, that's one of those things that as I was struggling to try to put in the chat, giving you the link to the report so that you can kind of understand a little bit how that might, you might be leveraging a microgravity environment for something that could be used on an on-ground, or even the reverse, something you learn on the ground that could be leveraged for in flight.
Okay, thank you. All right, let's do final question. Does the advanced manufacturing subtopic solicit full closed loop real-time monitoring and control solutions, or are individual enabling component technologies appropriate?
Can you give me that first part of the question one more time, please?
Does the advanced manufacturing subtopic solicit full closed loop real-time monitoring and control solutions, for example, sensing and processing, control and correction, or are individual enabling component technologies, for example, real-time sensor technology, appropriate?
So we're looking more towards the development of using those individual sensors to develop a multimodal sensor that can give us that closed loop control that we're looking to develop.
Great. All right, thank you. I appreciate that there are a number of questions still remaining in the chat, so we will go ahead and get all of those questions answered following this session today. So please be looking out for the answered cues that you provided on the Ignite website. So we are at time, so that is all that we have time to answer today. Thank you all so much for joining. Thank you to our subtopic authors for providing overviews and great answers to the questions. Again, visit the Ignite website to see the solicitation and additional guidance. The solicitation closes on July 22nd, and join the Ignite Slack to stay in the loop. We look forward to seeing your proposals. Thank you so much, and take care.